All right, go.
All right, so we have a truss and we made sure we have a pin connection at this side and A. So you have AX and you would have AY here. And then on this side, due to it being a horizontal roller, it cannot resist any force in the X direction. So you would only have EY here. And so we had our weight centered at C hanging with a rope, 5 pounds. And so I did sum of forces in the X and Y direction. And you realize using symmetry, or you can use moments around A or E with whatever you'd like, you realize that the reaction of both would be 2.5 pounds force due to symmetry or due to the moment. Either you could calculate and get the same answer, and you come to the conclusion that AX is 0 because there is no horizontal force that can be resisted here, so it has to be AX equals 0. So we first start our calculations at the A joint. We're using the method of joints to solve this, and we have AX, AY, B, and then C. And first, what we always do, I do sum of forces. And so I did sum of forces in the Y direction. So you have AY and you have ABY. And you understand this, ABY has to be negative 2.5 lbf because it's the only member acting in the Y direction here. And so that means AB is in compression. And then we do sum of force in the X direction. You have AX, which is 0, ACX, and ABX. And since we know AB is in compression, we must know AC must be in tension to resist the X force, the negative X force to the left. And so once we use symmetry, because we know the symmetry of 22.5 here, and then 30.75, and cut that in half to get the adjacent side, and then the hypotenuse, and then we can calculate the triangle as seen here. And so we use geometry to then get that ABX is negative 2.340 because it's in compression, and then to counteract that, ACX must be 2.340 pounds force. And then, since we know that, we will move on to section our next joint, B. And we already know AB, we have AD, and we have BE. And so we know we can solve this, since we only have 2 unknowns and 2 equations. And so I do sum of forces in the Y direction. Only BE and AB can act in the Y direction. And I already know BCY must equal 2.5 pounds force due to the geometry is the same as the other one. And you can also just calculate that out here because you know it must equal. And so we also got BC equals 3.42 lbf, just like we got AB is equal to 3.42 lbf. But this is in compression and this is in tension to counteract the Y components here because they're the only things acting in the Y direction, so they must counteract each other. And that makes sense intuitively. If the top chord is in compression, then these members have to be in tension. And so next, I then did sum of forces in the X direction, and so you have the negative ABX, and then B, this should be BC here, and then you have the BD to the right as we've drawn it. We drew them all in tension, even though we know this is in compression, and then this is most likely in compression.
Why do you do the tension? Why do you put it in tension?
Because it just simplifies it when calculating.
Okay.
And so you have BCX to the right here, and you have ABX to the left here, and then BD. And so we know this is negative, so you have negative, sub that in there, positive, plus BC here. So that would make sense that it's 4.68 once you move it to the other side and it's negative. So thus BDX would also be in compression, which makes sense intuitively as it is the top chord of the truss. And so we got BC equals 3.42 pounds force as our final answer in the joint. And this was the joint that we measured here.
So what we'll do here in a second is we'll fire it back, the video up again, and we'll show our mock. But this is our theoretical, what we should get. So we'll go back and actually show the fish scale and what we got.
And this is our final calculations showing which is in tension, which is in compression. And you understand we didn't need to solve the other side of the truss because it is symmetrical and the load is in the exact center of the truss. So that would mean the force in the members on the other side would be equal to the ones we just solved.
Yep. All right, so when we fire this back up, we will be at our actual scale model.
I started.
All right, so where we left off, we had already given the calculations. So this is the mock-up that Noah and I built. So we made it out, or we cut the members out on a laser cutter. And then kind of stuck it together here. We put the connections through a bolt in each side, and then you can kind of see here that we've locked the roller in place. So the only way it can move is horizontally in the X direction. So we also have our weight here at the member, and then we've replaced one of our members that was cut out with a fish scale. So, and then you could kind of see, we'll talk about a little bit here in a second. The only thing here that's going on per the request or that we talked about with Professor Sisk was just keeping it from being able to fall over. So this isn't holding on to anything. It can be moved. Outside of that, it's not being interacted with. It's just being held up in place so it's not tipping over. That being said, from our calculation we found that it was supposed to be 3.42 in tension. So the reason we put ropes here is because the only way that a rope can be calculated correct, have a force is through tension, yeah. So we replaced the member, tied it to one of our joints, tied it to another one of our joints, and then we ended up getting around 2.5, 2 point something in tension. So there's a margin of error with these fish scales, so that's where we're at. Plus it's got a little bit of, well, you could tell some other stuff is going on. But with 3.42 being our actual number, I'd say this is pretty close to what we can get. Outside of that, here's the whole thing itself. Noah and I realize that statics is an idealistic situation, and often the real world doesn't mirror our perfect calculations. We make a lot of assumptions, we ignore a lot of things. That being said, one thing that Noah and I would have changed if we would have done this project all over again was to make it out of wood. We had a lot of issues with getting it propped up to stand right without putting it in a bind, so it caused a lot of headache. Ultimately, we should have used the KISS method. It is what it is. That being said, Noah and I did learn a lot of things, and I hope you enjoyed our project and all the math and all the other little nuanced stuff. Thanks.